SwayamPrabha. Digital India. Educated India.
Welcome back. We were discussing the mass and energy balance of control volume. In this lecture, we're going to continue our discussion on steady flow devices. So in particular, we will discuss pipe and duct flow and as well as energy balance for general unsteady flow processes. So pipe and duct flow are very common in our daily usage and it's very important in many engineering applications. So a simple flow through a pipe usually satisfies the steady flow condition. This is an example of hot flowing through a pipe, and the heat transfer in such a conditions are quite significant. A typical pipe or duct flow may involve many form of work. So this is an example of electrical work and as well as the shaft work in this pipe flow. So what is the energy and mass balance for a simple duct flow? We'll take one particular example to understand it. So this is an example of electrical heating system which is used in many houses. Okay, so you have a simple duct with a resistance heater. Okay, and there is a electrical work of power of 15 kilowatt which is supplied to this flowing fluid, and this is the air which enters here at 150 meter cube per minute at 17 degrees Celsius with a certain volume rate, which is of course 150 meter cube per minute, and there is a heat loss of 200 watt, and what we need to find is the exit temperature of the air. So we'll go with the simple mass balance considering is a steady flow. Of course M1 here dot should be M2 dot, which is here at 2, and this is 1, and this should be M dot. Okay, considering steady flow condition, the in dot out, that is net energy transfer to the system, would be 0 because this is a steady flow condition. So this is what you get in E in dot is equal to E out dot. Okay, now what is the E in here? E in is a so work in and the heat supplied to the system and the work supplied to the system plus the energy of the flowing fluid which is here. That is you have W dot in plus Q dot in plus summation of M theta in should be equal to your W out in plus Q out plus summation M theta out. Okay, so this should be here. Okay, now since there is no Q in, so what you have as far as the E in is concerned is W in, so that is W in. Assuming your KE plus PE is 0, okay, you have W in plus only the enthalpy of the flowing fluid as a part of your energy of the flowing fluid, that should be equal to the E out, which consists of heat out, which is this, plus the energy of the flowing fluid at the exit condition. So this further can be written in this form. Okay, so this apparently is nothing but M dot H2 minus H1 considering air as an ideal gas, and we know that delta H is nothing but Cp delta T. Okay, so this is what we can write this expression in terms of Cp. So this is going to be a simple energy and mass balance for a fluid flowing through a duct having a certain energy transfers and as well as the work interactions. Okay, so now we'll look at the systems which are considered as unsteady flow processes, because there are many processes of interest which involves changes in the control volume properties. So for example, you have a charging of a rigid tank from a supply line in an unsteady flow condition, which essentially means that the control volume properties or the control volume undergo changes with time, and such kind of changes would be part of your unsteady flow process. Now such process is also sometimes called transient flow process. So the examples of course is one which we have highlighted here, which is a charging of rigid tank from a supply line. Other could be a discharge of a fluid from a pressurized vessel, and as well as, for example, the inflating tire or balloon. Now, for unsteady flow condition, the shape and size of the control volume may change along with time. So this is an example. So you have a flow through this opening, and the control volume size can undergo change, and because this volume or this particular piston can move up as the fluid during the transport of the fluid to the control volume. Now, most of the unsteady flow process can be considered as a uniform flow process. The definition of uniform flow process is the following. Fluid flow at any inlet or exit is uniform and steady, okay, for such uniform flow process, which essentially means that let's say if you have a charging through a pipe, okay, so what we are assuming, if this is our control volume, okay, the properties here is uniform and steady, okay, and thus we can approximate this unsteady flow process as a uniform flow process, okay. So thus the fluid properties do not change with time or position over the cross section of an inlet and exit. Even if you consider, let's say, because this is an approximation as far as the uniform flow process, in practice the temperature and other conditions may change across the cross section. So what we are going to consider is we're going to take an average value, okay, for such a condition. So if the properties do change, we are going to treat as an average and as a constant for the entire process for our analysis. So this is a simple mass balance for this particular non-uniform flow process. So M in minus M out for within the control volume is simply change in the mass of the system, and the mass of the system change can be written as simply the final value of the mass minus the initial value of the mass, okay. You can write this M in minus M out as simply M inlet minus M exit. This should be simply M2 minus M1 of the control volume. So this is a simple mass balance. Okay, what about the energy balance? We will start again by the general energy balance, which is nothing but the net transfer of energy to the system due to the work, heat and the mass flow should be equal to the net changes in the energy of the control volume. Okay, and that would be change in the internal energy, potential energy of the control volume of the system. So here this is our basic definition of the energy balance, and this E in this case we are going to consider Q in plus W, any work interaction if at the inlet condition or the heat transfer to the control volume or system, and the work done on the system plus the energy of the flowing fluid inlet at the inlet condition minus Q out plus W out plus the energy of the flowing fluid. This should be equal to change in the energy of the system, which includes your internal energy, potential energy and other energies. We can go back to the earlier definition of theta here. So theta was the energy of the flowing fluid per unit mass, which is given here. So this is enthalpy Ke plus Pe, and E was the energy of the non-flowing fluid, which is defined here per unit mass, okay. Now assuming Ke plus Ke and potential energy to be negligible, if you assume that, and not only for the fluid but as well as for the control volume, then we can write this as a net energy, net heat supplied to the system minus the net work done by the system is equal to the change in the flowing energy plus that of the system, or change in the energy of the system. So essentially what we have done is Q in minus Q out becomes the net heat in, and W out minus W in becomes net work done, okay. That should be equal to the change in the flowing energy, okay, which means we are taking this to this side and this to this side, and then we got this expression, okay. So this is your final energy analysis of unsteady flow process. Now just take a specific case here. In case of the exit and inlet conditions are closed, this energy balance would turn out to be energy balance for a closed system, okay. Typical unsteady flow process may involve different work, not just shaft work, but it can also include electrical work and as well as boundary work, so that we have to keep in mind, okay. This is an example here, illustration here. Okay, we'll end this particular lecture with an example. So this is an example of insulated 8 meter cube volume, okay, which contains air at 600 kilopascal at a temperature of 400 Kelvin, and there is a discharge when you open the specific valve, and there is a discharge and the pressure starts dropping, it drops to 200 kilopascal. The temperature of this particular air is maintained constant by an electrical resistor, and what we have to determine is the electrical energy supplied to air during this process. So let's start with simple mass balance here. So mass balance here would be like m in minus m out is equal to delta m system. Okay, so now this m in is 0 and this is nothing but exit. E stands for exit, and this will be m2 minus m1. So m2 and 1 are defined as the state, initial state and the final state of the system. Thus your me is nothing but m1 minus m2. Okay, now what is the energy balance here? Energy balance would be here is En minus E out. So this is the net energy transfer to the system, and that will be delta E system. Okay, so E in this case is nothing but W E in. Okay, there is no specific heat transfer to the system, minus what about E out? Now E out, there is no Q, there is no KE, there is no PE, so this would be considered 0. So the exit E out would be only due to the energy of the flowing fluid, which essentially means this is nothing but m E theta E. Okay, and this would be simply the internal energy of the system at 2 minus 1. So this, since the mass is varying, is initial and the mass would be different, so this has to be written as m1 u1. So this is our energy balance. Okay, now we need to find out first of all what is m2, m1 and me. Okay, so what we are going to do is we will consider air as ideal gas, and hence m1 should be simply p1 v1 by r t1, and m2 is nothing but p2 v2 r t2. So let's see what is p1. P1 is of course 600 kilopascal. The volume is already given to you. Okay, we can get r from table A1. So this is 0.287 kilopascal meter cube by kg Kelvin and 400 Kelvin. So this comes out to be 41.8 kg. Okay, and this similarly you can also calculate m2. On the m2 only the change is p2, which is 200 kilopascal. Okay, here, and thus you should be simply 13.94 kg. Okay, so the next thing is that me is nothing but m2 minus m1. So this is straight away, because we have already calculated m2 and m1, so this comes out to be 27.87 kg. Okay, so now we need to find out h and u. Okay, the particularly h, e and u1 and u2, and this we need to make use of the table A17. Now what is given here is always at 400 Kelvin, and as we know, for an ideal gas enthalpy is only dependent on temperature. So it's for this particular system u1 and u2 should be same. So 400 Kelvin, h is given here and u is already here. So h1 is nothing but 400.9, which is this kilojoules per kg, and u1 is nothing but same as u2, which is 286.16. Okay, now you can make use of these datas. Okay, in your energy balance, which was nothing but this, which I am writing again here, plus m2 u2 minus m1 u1. So you know this information, you know he. Okay, you know this m2 m1 n1. So thus you can calculate your electrical work, which is nothing but 200 kilojoules. Okay, so this is how we solve a problem making use of the table for the case of unsteady flow process. If for example in this case we have maintained the temperature at 400 Kelvin, if there was a case where the temperature was changing, then so let's say initial temperature could have been T1 and the final temperature could have been, let's say, T2, then what we could have done is at the exit condition we could have calculated HE at T1 plus T2 by 2. So to evaluate the property, and this would have given reasonably accurate calculations in terms of the values. Okay, so that would be the end of this particular module, which was on the energy and mass balance of a control volume. Okay, so what we have done in these 5 parts, we have looked into the conservation of mass, okay, where we consider the mass and volume flow rates. mass balance of a steady flow process, incompressible flow, and flow work and energy of a flowing fluid. Okay, we have also looked into the energy analysis of steady flow systems, and we have taken examples of various steady flow energy engineering devices. Okay, and in this particular lecture we looked into the energy analysis of unsteady flow process. So that will be the end of this particular lecture. In the next lecture we will start a new topic which will be on second law of thermodynamics. So I will see you in the next lecture.